Good day, one and all. You are welcome to the HESA video bank, also called the HESA e-library. Today we are talking about glycols and organic chemistry too, right? And then we'll talk about the preparation of glycols, the properties of glycols, and the reactions glycols undergo, right? Now, the question is that this is a supplementary material, not an alternate material, right? So without much ado, let's just go in. Now we are saying glycols are compounds that contain hydroxy groups, right? They contain hydroxy groups on adjacent carbon. Now this is definition one. Let's take note of it. Now the next statement says that although glycols are alcohols, glycol chemistry varies in some respect to general alcohol, which makes sense, right? Now we are seeing the next statement, which is very important. A glycol is an aliphatic organic compound in which two hydroxyl groups are present. And so this is definition two. Now, the first one was saying that glycols are just compounds, right? Organic compounds, of course, that have carbon on adjacent hydroxyl groups on adjacent carbon. The second one is telling us that it's an aliphatic organic compound. We know aliphatic, right? We know aromatic, the opposite of aromatic, or what's at the other side of aromatic is aliphatic, right? So either it's a straight chain or it's cyclic, right? And we have cyclic aliphatic. So something like this will qualify as aliphatic. We've already butane. This aliphatic, right? Aromatic is the benzene type, right? Yeah, but they're benzene-like compounds. Now we are seeing it's an aliphatic organic compound in which two hydroxyl groups are present. Now the second definition is not stressing on the fact that the two hydroxyl groups should be on adjacent carbon atom. Now, these two definitions are correct. The reason why we pick the first definition is explained in the next statement. The next statement says that the most important glycols are those in which the hydroxyl groups are attached to adjacent carbons. Now, because we are concerned about practicality, we are not looking at just defining glycols, but we are looking at glycols that are important to us as pharmacists or as chemists, right? And because all the important one or the most important of the glycols always have the hydroxyl group being on adjacent carbons, that is how we define glycols. The first definition of glycols stand, but we can extrapolate it or we can open it up. Just that the importance to us in practice, the important ones are the ones that have hydroxyl groups on adjacent carbons. Very important. Now, if you continue, I said, and the term glycol is often interpreted as applying to only such compound, Now, the latter is called vicinal. So they have introduced another term to us, vicinal diols. This is not the first time we are coming across this concept. Now, if I have two adjacent carbon atoms like this, right, and then I have an OH here, right? Now, this is called a vicinal diol, right? If it's two adjacent carbon and I have a CO here, C and another CO here, right? This is also a vicinal dichloride. And so that is a vicinal. When you have adjacent carbons having the same group, that is vicinal, right? It's also called 1,2-diol. Now, the other side, if you flip vicinal, we have something we call geminal. Geminal is when you have the two equal groups on the same carbon atom, right? So if I have C here and then there's OH here, there's OH here. This is what we call geminal, right? Now, they are saying compounds in which the hydroxyl groups are attached to the same carbon atom. Geminal diols cannot be isolated, right? Just a point of information for us. Moving on. Examples. So they have given us the two most important examples that will come across in practice. The first one is ethylene glycol, because it has normal ethylene. So the ethylic group is here, right? Like normal ethene. And then we have substitution of two hydroxyl groups. Very simple. The next most important one that we'll meet is the propylene glycol, right? So this is the structure of propylene glycol. We have to know the structure. Right now, we are being asked to find out other glycols. Let me draw pentylene glycols. Let me use the skeletal structure because it has not come up, right? So skeletal structure, if you see a dot here, it means it's one carbon with all the hydrogens there. This is methane, right? We don't really draw methane using skeletal structure. So, but this is essentially methane. If you do this, right? Now, this side, this vertex, and then this point here, they are carbons with all the hydrogens substituted. So this is ethane, right? So if I want to draw pentene, right? I want to draw pentylene glycol. So first of all, I have to draw pentene. Pentene will just be some lines, right, with 5 points. So I have 1, 2 here, 3, 4, 5. Now this is pentene. This is pentene, right? So if I put an OH here, an OH here on adjacent carbon, I have pentylene glycol, right? So this is another example, just a point of information. Now let's go into what we are supposed to talk about. The first one is preparation. We'll talk about 2 different ways of preparing glycols, right? Now the first one is oxidation of alkenes with osmium tetraoxide or KMNO4. We can use both reagents, right? Good. Now, what we will have is, first of all, the reagent, an alkene. Now, let me define an alkene to us. The alkene is this portion, the C double bond C here. We call that part the functional group. The definition of a functional group is the part of the compound that is responsible for the reactivity of the compound. That means this whole reaction that we are about to undergo, even if you don't know anything, know that the changes in the compound will only occur where we have the C double bond C. The phenyl group here will not be affected. The methyl group here will not be affected because those are not the functional groups. The functional groups are the part that goes into reaction. That is why we call them the functional group. Actually, that's the definition of a functional group, right? And so the only part, I'm stressing on this because it will come up a lot. The only part of the compound that will change will be where we have the C double bond C. That is the only part that will change along the course of the reaction, right? So we have the alkene reacting with osmium tetraoxide. Now, the 2 arrows shows you that it's not a single step. There are a series of steps. In this one, essentially, we have 2 steps, right? So the first step will occur, and then you need this reagent. So if we are going through the first pathway of using osmium tetraoxide, we need 2 reagents, right? The osmium will react halfway, and now we have to add a reducing agent. Now, the 2 common reducing agents that we use, right, is that we use hydrogen sulfide, or we use sodium bisulfite, or sodium hydrogen sulfite. What we have here, this is what I'm talking about. This is sodium hydrogen sulfite. It's the same thing as sodium bisulfite, right? So that's what we have to add before finally we can get our glycol. Now, at this point, I want us to understand how the glycol is formed from the alkene. Now, this is not the mechanism. We'll talk about the mechanism. But apart from the mechanism, we have to also know how we can transition the reagents to the product. So if you want to get the product from this one, what you have to do essentially is that you have to break this double bond. I told you that the reaction will occur where the double bond is, right? Now, the reaction that the unsaturated compounds undergo is addition reaction. Addition is we break one of the double bonds. That is essentially the one that is forming the pi bond, right? Break it, and then this carbon will now have a chance to form an extra bond. This one will have a chance to form an extra bond, right? You put an OH here, you put an OH here, you have formed your glycol. That is that. So that is what we have here. Very simple. Now, if we read down, they are saying glycols are obtained by a reaction of aqueous potassium permanganate. Now, into brackets, pH greater than 8. I have to explain this. Now, KMNO for a common reagent, right? A very common reagent is a very powerful oxidizing agent, but it doesn't act alone. The power of KMNO4 depends on the solution in which it is in. And so KMNO4 can be used in an acidic medium. KMNO4 can be used in a neutral medium. And KMNO4 can actually be used in what? In a basic medium. If we say aqueous potassium permanganate, pH greater than 8, it means we are talking about what? KMNO4 in a basic medium. Now, why do we have a basic medium? Essentially, the difference between it being an acidic medium and a basic medium is when it's in an acidic medium, it is a strong oxidizing agent. So we'll use that when we desire very strong oxidizing power. But when we want a mild oxidation, we have to use it in a basic solution. That is that. So it means in this context, we need KMNO4 to act as a mild oxidizing agent. Mm, mm, mm. right? So now we are saying that's all osmium tetraoxide in pyridine solution. Now, pyridine would be the solvent, right? Will be the solvent to help solubilize the osmium tetraoxide. Now, these two reagents can both be used. I'll explain why they can be used, why we need these two reagents in this particular reaction. But both of them have advantages and disadvantages. If you take the aqueous potassium permanganate, right? Now, the advantage is that it's a very common reagent, is easily available or readily available. Now, the downside of it is that it is inherently, it is a strong oxidizing agent and can further oxidize the glycol, which we don't desire. So sometimes we get poor yield because of the further oxidation of the glycol. This glycol can be further oxidized to an aldehyde or a ketone, and which can also be further oxidized to a carboxylic acid. So because of the further oxidation, I mean, that is a disadvantage or a drawback of KMNO4. Now, osmium tetraoxide, the advantage is that it gives you a higher yield because essentially it is a weak oxidizing agent. So you get a higher yield in pyridine, right? You get a higher yield. Now, the downside is that it is toxic. Osmium tetraoxide is a toxic reagent, which poses a serious health risk to the one performing the experiment should serious protocols not be maintained, right? So that is that for that. Now, we are saying that both reaction appears to proceed by the same mechanism shown below. So we'll talk about the mechanism. Now, we are saying that is the metallocyclic intermediate. Now, I'll talk about the metallocyclic intermediate, but now the point here is just a point of information. They are saying the metallocyclic intermediate may be isolated in the osmium reaction. Point of information. Now, we are saying in basic solution, the purple permanganate ion is reduced to green manganate ion, provided a nice color test for the double bond functional group. So this is a point of information. Now, what will happen if you're using KMNO4, right? What will happen is that in the KMNO4, the manganese is +7. That's the oxidation state of the manganese. Now, in this particular reaction, it will be reduced to +6, right? It will be reduced to +6, which is a green color. So you will see a color change. So a very simple test checks whether a compound has a double bond or unsaturation, right? You can use KMNO4 in the basic medium, and then you get that color change. That color change confirms that there's a double bond or there's an unsaturation in the compound. So it's a very simple test that we do, right? Yes. Now, the specific color that will appear will depend on how you are using the KMNO4. Essentially, if you're using KMNO4 in acidic medium, after the strong oxidation, you get Mn in +2 form, which is colorless. So even the color change that you will see, sometimes you get KMNO4 in brown color, which is +3 or +4, right? So even the color change that you see depends on the medium or depends on the type of oxidation occurring there, right? But in this particular reaction, we are just moving it to the green color, that is +6. And we'll see that when we go to the reaction. Let's explore the reaction down there. Right, so this is essentially the whole mechanism or reaction pathway. Now you have the alkene. Now this is the only part of the compound that will go into the reaction. That is why it has been shown. All the other groups are R and will remain R, will not change, right? Good. Now if you go through the step on top here, we have the ion, the MnO4 ion in basic solution. Is of course is aqueous, right? So now you get your metallocyclic intermediate. And then it will further proceed to give you your glycol. And then this is the green MnO4 2- with the manganese being +6 here, right? Now, if you come down here, if you use the osmium tetraoxide in pyridine, you get your intermediate, which is also a metallocyclic intermediate, right? But then you can't forget about this. You have to further reduce it. Further reduce the intermediates. Further reduce it with either the common ones are hydrogen sulfide or sodium hydrogen sulfide or sodium bisulfite, right? Then you get your glycol. Now, there's an important point here that I have to read before I explain why these two reagents are used in this particular reaction. Now, we are seeing that permanganate and osmium tetraoxide have similar configuration. in which the metal atom occupies the center of a tetrahedral grouping of negatively charged atoms. A lot of English, but let me draw the structure of permanganate and then osmium tetrahydride, and you understand what we are saying. Right now, this is the structure of MnO4 minus. So Mn now, right? This is it. If it's KMn, then we are having this, right? So this is MnO4. Now this is osmium, OS. So this is osmium tetrahydride. Now, if you look at these two, this permanganate ion and then this osmium, they all have the same shape. They all have essentially, they have the same shape, right? They have a metal which occupies the center of tetrahedral grouping of negatively charged atom. Now, it is this particular configuration that will enable them to form this metallocyclic intermediate. This is why these two are used. This is why these two are the reagents, right? Because these two are not the only oxidizing reagents, but the reason why they can be used in this particular reaction is because of their inherent configuration, which allows them to form the metallocyclic intermediate. Mm. 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 So that's it, right? Now, if you look at, you don't have to chew the structure. If you look at the structure, essentially what has happened is that the O here, right? So the double bond here has broken so that a new bond can be formed between the carbon that initially bore the double bond with this oxygen, and then this one too will break, right? So that this oxygen can form a new bond with the carbon that had the double bond. So that is what we have here, right? Now, we don't see the negative here, right? But we see dots, dots here because this negative charge has been delocalized. So that is what we see up here, right? Yes. Now, if you come to the osmium side, that it doesn't have any negative. So what will happen is just this bond will break and form the bond with one of the carbons, right? That had the double bond. This one of the double bond will break. This oxygen will form a bond with one of the carbon. The double bond here too will break, right? So this is what will give us this the intermediate here. We don't have to choose these intermediates. Very simple to draw. Now let's go on. The second way. Now the second way we see is acid catalyzed reaction of water with epoxide. That is the less technical way. The more technical way is acid catalyzed hydration of epoxides, right? Now, this is epoxide. So the epoxide functional group, very simple, right? Now, the whole pathway here has given us the mechanism, but the mechanism is not well split out. And so I would have to split out the mechanism again for us. So I'll split out the mechanism. But what we have here is essentially the epoxide, right, reacting with an acid, which is a catalyst. That is why we start with this acid and then we end with the same hydrozonium. Yes, this acid, hydrozonium ion, the acid. Now, the first step, what happens is, let me open this hydrozonium ion up. This is the configuration of the hydrozonium ion. H, 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 and there's a plus here. Right now, this double bond here will come and take this hydrogen, will come and pick this hydrogen, and then this bond will break onto this oxygen, right? So this is protonation of the oxygen, right? And so now the oxygen will now be coordinated to this hydrogen and a plus sign will be here. So that is what we have seen here. And then when the bond breaks onto this oxygen, it forms water. That is the water side product that we have in the next step, right? Now in the next step, always the electrons on the oxygen, or the electrons are the ones that attack. So the arrows move from the electrons to the carbons that they are attacking. And so what will happen here is that because of the positive charge that has been deposited on this oxygen, the bond here will break onto the oxygen. The bond here will break onto the oxygen to stabilize the positive charge. Now, at the same time, because this carbon is about to lose a bond, the water here, the lone pairs on the oxygen of the water would simultaneously attack this carbon. And so in the next step, what we'll have here is finally this bond has broken. So there's no positive charge again on the oxygen here. But this water has been coordinated to the carbon, right? Now, what will happen in the last step, which wasn't also shown, was that water will come and they remove one hydrogen. Let me draw the same thing again. The OH2 plus, I can bring one of the H here, bring one of the H here. The plus will still be there. Now, when we have water as we have here, the lone pairs of the water will come and attack this hydrogen. When they attack this hydrogen, the bond here will break onto this oxygen. So in the last step, you realize that the plus on the oxygen here has been neutralized because of the breaking, right? And then the water here has taken hydrogen to become hydrozonium ion. So once we start with hydrozonium ion and end with hydrozonium ion, what we have here is a catalyst, right? Because the catalyst is not supposed to change at the end of the reaction. It's supposed to only facilitate or speed up the reaction. And this is the glycol we have. Now, if you want the comprehensive mechanism, you have to split it up just as I did. Because even though this is a mechanical pathway, there are some parts which are condensed. Good. So this is the second way. We can hydrate epoxides to what? To form glycols, acid catalyzed hydration of epoxides. Good. Now, the next thing, we are supposed to talk about properties of glycols. The first point is 1,2-ethane diol, that is ethylene glycol, a sweet, colorless, and somewhat viscous liquid. Now, this is where the question will come that will baffle me, right? Now, the ethylene glycol is a toxic liquid, so we don't take it, we don't consume it. And so, how did we find out that it was sweet? This is the question for you to go and ask yourself. I mean, it will not come anywhere. How did we find out it was sweet if it is toxic? Because it is toxic. So, who took it and told us it was sweet and died? That is the question for the gods. Right now, if you come to the next point, you are seeing 1,2-propane diol, which is propylene glycol. Right, its physical properties are quite similar to those of ethylene glycol. The next point says that the two OH groups lead to an extensive intermolecular hydrogen bonding. This results in higher boiling point, right? Of course, the hydrogen bonding between the molecules of the glycols are higher, right? They are higher because it has two OH groups, and each OH group can form a hydrogen bond, right? So they form more hydrogen bond, and then essentially they have higher intermolecular force, and that will result in a higher boiling point. That is what we can see here. Now, the next point is that they are completely miscible with water, and that is still because of the hydrogen bonding. The hydrogen bonding would help the ethylene glycol to coordinate with the water. So the interaction is still through hydrogen bonding, and then they will dissolve, right? Very simple. Two polar molecules interacting through hydrogen bonding to dissolve. Now, the point down there is that glycol is the main ingredient in many antifreeze mixture for automobile radiators. Why? Now, the explanation of this is interesting. Glycol, the ethylene glycol has two properties, right? It has a dual property. Now, when you add ethylene glycol to water, ethylene glycol will lower the freezing point of water. Essentially, what we are saying is that we know that the freezing point of water is 0 degrees. If you add ethylene glycol, the freezing point goes below 0 degrees, such that if your vehicle is moving in area or an environment which has a very cold weather, the water there will not freeze and destroy your engine. That is the first thing, the first characteristic. That is why we use it in antifreeze mixture, the first one. Now, the next character is that the ethylene glycol, when you add it to water once again, it increases the boiling point of water. So essentially, we know the boiling point of water is 100 degrees Celsius. When you add ethylene glycol, the boiling point gets higher than 100 degrees Celsius. And the reason why this is important is because when you're also driving your car in higher environment, higher temperature environment or hot weather, right? We don't want the liquid to evaporate. And so that's the important. We also add it to antifreeze because we want to increase the boiling point of water, which it does for us, so that when we are moving in very high or hot weather, or when the engine heats up right there, water will not evaporate. So these two properties are the reason why we use ethylene glycol as in antifreeze mixture, because it can decrease the freezing point and increase the boiling point, the dual property. Now, glycols and human. Although propylene glycol has the same properties, much like those of ethylene glycol, its physiological properties are quite different. We have already established that ethylene glycol is toxic, right? Propylene glycol is essentially non-toxic, and it can be used as solvent for drugs and as a moisturizing agent for food. Like other alcohols, propylene glycol is oxidized by the liver. Now, this is the oxidation process. We have propylene glycol being oxidized fully to form pyruvate. Now, pyruvate is a normal intermediate in carbohydrate metabolism, right? So it does not really cause a problem if we have this oxidation, right? That is why propylene glycol is non-toxic, right? When it's oxidized, the product it forms is non-toxic. It's a normal intermediate in carbohydrate metabolism, non-toxic. We don't have any issue with that. Now, this pyruvate, I would have talked about it, but it is a keto acid, and it will be captured in a different discussion. So we move on. Now, we are seeing glycerol, a product of fat metabolism, is essentially non-toxic, right? So now glycerol is another OH on this one, right? So let me just show you glycerol, another OH on this one. You have to remove one of the hydrogens too, right? So it's like the propane with the OH on different carbons, right? And we are saying it is also non-toxic, right? Reactions of glycols. Now we'll talk about two main reactions and we'll add one extra reaction, right? So just three. The first reaction is called periodic acid oxidation. Now we are saying the periodic cleavage reaction has been used to test for glycols. The general equation for the oxidation is shown below. So the first one we have here, now we would correct this thing again. What we have here is called periodic acid. I said we'll correct it, right? And when you add this periodic acid to the glycol, what we have here, what we form is we form two carbonyl compounds, an aldehyde and a ketone, and then we have the byproduct. What I want us to know here is how we can transform the glycol to the ketone or aldehyde. And then we will stand at the same spot and we'll learn how to convert the aldehyde and ketone back to the glycol. So this is chemistry. People say it's a science, which is true, but chemistry is also an art. And so now what we are coming to do is pure art, not science. Follow the art. What will happen here essentially when we add the periodic acid is that first of all, there will be cleavage. Now, before I show you the cleavage, I'll have to show you the functional or the functional unit in the compound. The functional unit in the compound is this. This is the functional unit. The CO bond here and the CO bond here. Now, these are the two most important units. And so the reaction will occur within these functional, between these functional groups or within this functional units. What will happen, first of all, is that there will be cleavage between these two important units. So cleavage. Now, after this cleavage, this side is different from this side. These are two different sides. Then what I will do again is that I'll remove this hydrogen and then introduce a double bond here. That is the compound we have here. You can check. The pH is here, pH is here. The H is here, the H is still here. This H is still there. The carbon, now it still has the O, but now it's a double bond O, and then we cannot see the hydrogen. If you come to this side, the same thing after the major cleavage, what you do is that you remove the hydrogen here and you bring a double bond here. Now, this compound is what we have here, right? This compound is what we have. The CH3 here is the CH3 here. The CH3 here is the CH3 here. And then the C double bond O here is what we just formed in the middle. This is what we have. Now, this is how you can form your products. Now, we have to essentially learn how to also convert the product back to the reactant. We have questions that we'll solve at the end of the discussion. So let's go and do that. Now, if I have these products and they have told me these are products from the periodic acid oxidation of a glycol, And so I should predict that glycol. This is what I would do. First of all, I would have to recognize that the two most important groups which were linked initially in the glycols are the ones that bear the carbon or the double bond O. Those are the carbons. And because in an attempt to form the product, I cleave that bond. In an attempt to form the reactant, I have to connect those carbons again. So what I will do is, first of all, connect this carbon to this carbon. Mm, 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 mm. Now, after connecting these two carbons, right, I would remove the double bond here, add an H, clean the double bond here, just one of the double bonds, the pi bond essentially, and add an H, and I am done. Now you can write it however you want it. Just that what you have to do is that this carbon should be directly bonded to this carbon. It has OH. Then around this carbon, which is the first carbon here, we have PH, and I have an H, right? Around this carbon, which is the next carbon directly bonded to this, it has OH here. Now it has CH3, and then it has another CH3. This is my reactant. This is how we do the prediction. Now, there are lots of sciences there, but let me quickly run to the last page and then we'll solve some questions, right? So that we don't forget the concept. Let's quickly run to the last page and solve some questions. There are questions on the last page. Quickly. Let's quickly do that. So on the last page, we have these two questions. The first question is, give the products expected when each of the following compound is treated with periodic acid. Good. So this is the compound we have. For better understand, let me redraw the compound. Now, the compound is actually very simple. What you have to know is that this carbon bears the OH and this carbon bears the second OH. So what I have to do is to cleave this bond. Cleave it. Now, when I cleave it, I'll clean this hydrogen and make a double bond here. So my first product, if I want to name it, is PH, CH2, C, double bond O, then there's an H. That's my first compound in essence. Now, second compound, this side, so I'll remove this hydrogen and bring a double bond. Now, that double bond is between this oxygen and this carbon. It's not between the oxygen and the hydrogens. So essentially, the product B would be, you can write it like this, C double bond O, H2. Yeah, right. You can write it like this, C double bond O, H here, and then H here, right? This is also right. You can write it anyway. You are right. You can even write it like this, CH2O. Right. This is also correct. This is also correct. So you can write anyway, and then that is that for that. Now the second question here, we are supposed to do the same for this. So these are the two carbons that bear the O groups, right? So I have to cleave it, cleave it, cleave it. Now when I cleave it, I'll clean this hydrogen and bring a double bond. Remove this hydrogen and bring a double bond, and I've gotten my product. Now, they are ideally, or for the other instance, there were two products we are getting, but this is one product because a ring structure, and these two are still connected. So if I am being very lazy, this is how I'll draw my product. Still the same hexagon, the same hexagon. At this side, I would have O double bond. At this side, I will have O. And this is correct. But this is not how a chemist would draw his compound. So let's look at how we can draw the compound. Essentially, we can draw 1, 2, 3, 4, 5, 6. So this is this same ring being spread out, right? And then at this side, we'll have double bond O. At this side, we'll have double bond O. Right? This is the actual compound. This is how it's supposed to be. This is how it's supposed to be. So that is it. But if you draw it like this, you are correct. Right? Nobody can mark you wrong. Now, the next set of questions said, what glycol undergoes oxidation to give the following set of products? So now they have given us the products and they have asked us to predict the reactants, the glycols that went this process. So what we have to do, first identify the carbons that bear the double bond O. Now, this is the carbon that bears the double bond O. This is the carbon that bears the double bond O. So I'll connect them. When I connect them, then I'll clean the double bond here and add each, clean one of the double bonds here and add each. So essentially, I'll have something like this. DC directly bonded to this carbon. There's the cyclopentene group here. right? Then there's CH3, CH3, right? Now, what I'll have here is OH, and then what I'll have here is OH. I'm done. That is that for that. You don't have to even think about it. This is not science. This is art, real art. Good. Now, when you come down here, the two carbons that have the double bond O, and we have one here, we have one here. So what I do is I'll connect them, and then remove one of the double bonds here, add H, remove one of the double bonds here, add H. Once again, this is not science, this is art. If I'm drawing the structure, this is the structure. Right. And so I'll first of all connect these two. Then this one will be OH. This one will be OH, right? Very simple. You don't even have to think about it. You just have to know how to draw. The chemist is an artist. Good. That is that for that. Let's quickly go up and read the sciences behind the periodic acid oxidation. The sciences behind the periodic acid oxidation. So, yes, we are saying the formulas HiO4 or H5IO6 into bracket para-periodic acid are used interchangeably for periodic acid. It's sodium salt, NaIO4, sodium metaperiodate is also sometimes used. Now let me explain. When I was talking about this one, I said let's take this as periodic acid for now. Essentially, what we have here is called paraperiodic acid or autoperiodic acid. Same formula for paraperiodic acid or autoperiodic acid. That is why we have the paraperiodic acid in brackets. So that is the exact name of that. The H5IO6 is para or autoperiodic acid. And this one, the HiO4, is called metaperiodic acid. Metaperiodic acid. So the names are different, but all of them are periodic acid in me, whether they are meta, para, or O2. I mean, they are still periodic acid. So we use them interchangeably, right? Now, when you look at the salts, the salt here is coming from the metaperiodic acid. That's what we call it, the sodium metaperiodate. So this shouldn't be confusing. Just easy. When you understand the chemistry, these things are very easy. Now, the next point says the vicinal glycols are cleaved to aldehydes and ketones inhaled by the action of lead tetraacetate, lead-4 acetate. So they have introduced another reagent that can undergo the same reaction apart from the periodic acid. Now we are seeing that these two reactions are, now look at the English here. Look at the English here. This is also art. This is not science. We are seeing that these reactions are most efficient when a cyclic intermediate can form with iodine or lead linking both oxygen atoms. The ring then fragments, so they are describing the process to us, then fragment with breakage of the carbon-carbon bond and formation of carbonyl group. Now, what they are saying is that if the intermediates or if the glycols align themselves such that we can form a cyclic intermediate, we get a more efficient reaction. Now, that will mean that the process can occur in a non-efficient way or in an inefficient way without the cyclic intermediate, but it can still occur. So that point is telling us something that will make the process more efficient, but something that's, but the process can still occur without it because there are inefficient processes that occur every time. So the last statement will make sense. The formation of the intermediate is, however, not a necessity. It only increases the efficiency of the reaction, but it is not a needed step. And it would also make the next statement make sense because they are saying as a rule, cis glycols react more rapidly than trans glycols. Now look, the cis glycols will be the glycols C double COH at the same side. Now the trans will be like the COH at the side and then COH at the side, right? Now you realize that the cis can form the cyclic intermediate. And forming the cyclic intermediate gives a more efficient reaction and hence the faster rate. The trans, on the other hand, cannot form the cyclic unless, of course, they rearrange. There's a rotation to form the cis one. Before now, they can form the cyclic two. So now it is not as fast as the cis. That is what we are saying. This is art. This is not science. This is art. Mm. 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 Now, this is the process. Let's quickly run through the process. We have the vicinal glycol. If you pass it through the periodic acid pathway, this is meta-periodic acid, we will get the intermediate, the cyclic intermediate, and then it would further go on and then form this one for us, right? These are the two aldehydes that we have in place. I've shown you how to get your aldehyde product. You cleave these two bonds, right? Remove this hydrogen double bond here, remove this hydrogen double bond here. That's exactly what has given us. And the side product will be the iodic acid. Now, if you use the other pathway, which is by using lead-4 acetate or lead tetraacetate, now you get your intermediate cyclic, and then you get your two aldehydes, the same product, right? Now, the side product is lead-2 acetate or lead diacetate. Very simple. Very simple. Moving on. Pinnacle rearrangement, my favorite. Now, it is a form of 1,2 molecular rearrangements. It is at this point that I have to remind you of what you already know in chemistry, that reactions always proceed, at least spontaneous reactions. They always proceed towards a place that will give them higher stability. Natural reactions occur leading to higher stability. That's spontaneous reactions. And so we are saying carbocation would typically undergo rearrangement reaction from a less stable structure to an equally stable or more stable one by migration of an alkyl or hydrogen to the cationic center to form a new carbocationic center. Now they are describing what we call an alkyl shift or a hydride shift, something that we call an alkyl shift. Technically, we call it skeletal rearrangement. The reason why the skeletal rearrangement will form or will happen is to lead to a more stable intermediate, a more stable ion. And so what happens is that if I have a primary carbocation, there might be rearrangement to form a secondary carbocation. If I have a secondary carbocation, sometimes there's a rearrangement to form, that is if it's possible, a tertiary carbocation. That is if we can move just a single alkyl hydrogen group to get us that. Now, sometimes I have a tertiary, but I can still shift either an alkyl group or a hydride group to get the positive sign on a carbon, which is better stabilized by a substituent. So once there can be a single shift, a 1,2 movement, a 1,2 molecular rearrangement, a 1,2 skeletal rearrangement to give me a more stable product, it would happen because reactions always happen to lead to the formation of a more stable intermediate or product. That is why spontaneous reactions occur. More stability. Reactions are looking for more stability. And that is what happens in life. Human beings are looking for more stability. At least sane human beings are looking for more stability. I can see from now that chemistry is also life. Let's read. The 1,2 rearrangement of carbocation, carbanium ions occur quantitatively only. Now, the first point is if the new carbanium ion is substantially better stabilized electronically by its substituent, than the old carbenium. Now let's take note of the first reaction here. So the first point here, because that is the point that will be of importance to us in the chemistry that we are about to talk about, the one down there. But the other ones we have to also bear in mind. But this first point, when there can be a rearrangement such that the positive charge will fall on a carbon, which can better be stabilized by a substituent. And that is what we will do. So we'll take note of the first point. The next point is, if the new carbenium ion is substantially more stable than the old carbenium ion because of other effects such as reduced ring strain. Now, ring strain always brings some level of instability in compounds. So if there can be a rearrangement so that the ring strain reduces, it is also something that we are looking at, something that can make the rearrangement occur. Now, the last but not least is, if the new carbenium ion is captured in a subsequent irreversible reaction. With these three in mind, let's talk about pinnacle. Now, pinnacle is a single compound. It's not even a class of compound. It's a single compound. It falls under a class of compound. We call them ditet glycol. Before the ditet is here, I'm not saying these things from my head, is here. Before the ditet glycol can even confuse, let's not confuse you. Di means two. Tet is tertiary, and glycol is what we have defined already. And so this is what we have. Now, look at something here. This alcohol, this OH, is tertiary. This carbon is tertiary because it's bonded to three other carbon. 1, 2, 3. Tertiary. So the alcohol here is tertiary alcohol. Now, if you look at this C here, it's also tertiary because it's bonded to three other carbon. 1, 2, 3. Right? So it's tertiary. So we have two tertiary alcohols, and the OH are adjacent atoms. So this is a diet glycol, dietitiary glycol, dietitiary alcohol. Right? And then we are seeing that pinnacle is the simplest. It's the simplest member. I can explain that, but let me not bore you with a lot of chemistry. Now, we are saying that the pinnacle rearrangement is an acid catalyzed dehydration. When we are saying dehydration, acid catalyzed, of course, dehydration also introduces temperature. It means you have to add heat, right, of glycols, which convert the glycols into aldehydes or ketones. So let's look at something. Right, so this is pinnacle. This is pinnacle in essence. This is pinnacle. Now, pinnacle, this is strong acid. Right, the strong acid is a catalyst, and then this is heat. Right, heat. And then we have formed something that we call pinnacolon. So the pinnacle undergoes the dehydration to form what we call pinnacolon. Now, this will be of interest to the pharmacist because pinnacolon is used in pesticides, fungicides, and herbicides. Again, pinnacolon is used to prepare the cyanoguanidine drug pinacidil. Again, pinnacolon is used in steripental, right, which is used to treat epilepsy. So, I mean, these points will make you know that we are not really learning the chemistry out of isolation, but because we need some of these compounds generated through some of these processes for some of the drugs which we use in treatment. Moving on. Now, we have to talk about the mechanism, the pinnacle rearrangement, because it's pinnacle rearrangement because we have pinnacle. But we'll go and exploit another mechanism before we now come and talk about the pinnacle rearrangement. So let's go and explore that mechanism and quickly come back. So we are seeing factors which can determine the cause of pinnacle rearrangement. The first one is the carbocation stability. I've talked about it. Now, the inherent shifting tendency or migratory aptitude of the different substituent groups. Now, we have steric hindrance and other ring strain. We have reaction condition. Of course, a dehydration reaction. We need to know the type of acid. Essentially, we need a concentrated acid. We need to know the type of solvent. Of course, in this particular reaction, we use water as a solvent. And then we have to also increase the temperature because it's a dehydration process. So the reaction conditions would also influence the whole pathway, right? And then the rearrangement involves 4 steps. So we have to go through these 4 steps. We'll define the 4 steps and then we'll come back. We'll come back and talk about the pinnacle rearrangement to form pinnacolon. So the first thing is protonation of one of the hydroxyl groups. Protonation of one of the hydroxyl groups. Now, as to which of the hydroxyl, because always glycols would have 2 hydroxyl groups. So as to which one of the hydroxyl groups will be protonated, we'll talk about it. The next one is elimination of water and formation of carbonium ion. We'll talk about that. The next one is rearrangement of carbonium to carbozonium ion. So this is a giveaway point, even though we've not talked about the mechanism. Now we are changing, we are moving from a carbonium ion to a carbozonium. The carbooxonium would mean there's an oxygen interplay here, and I will explain. The simple reason is that the carbonium ion, the carbozonium ions are more stable than, the carbozonium ion, of course, are more stable than the carbonium ion. That is why that rearrangement will occur. Very simple. Then there's deprotonation of the carbonium ion to form keto product. Now, this space has been left empty because that's the space to show the mechanism of what pinnacle rearrangement, which will come and show. We'll come and show. All right, so we are here. Now, this an example of the mechanism, right? So let's talk about this example. Now, the first one is we have this glycol. Now we can name this glycol. Let me name it. This is bonus. Bonus because you have watched the chemistry video. If you are naming, the parent name, of course, will be glycol, right? Or diol. So the important groups are this. This is phenyl group. This is the most important group. So this will be carbon 1. This will be carbon 2. Now I can decide to number it the other way around, but I'll defer some rules of chemistry. Let me try that and see. This is carbon 1. This is carbon 2. Now if I do that, of course, I have given priority to the groups that bear the functional group. But look at something. The phenyl will be attached to carbon 2. So my substitution, I would have 1 here, and then I would have, 1, 2, 2. So if I'm naming it according to the yellow ink, my name will be 2 phenyl, 1, 2 ethene diol, or I'll say 2 phenyl ethylene glycol, 2 phenyl ethylene glycol. Now, if I change the numbering to what I have in the red ink, I'll have 1, 2. Now, if you look at the other name, if I have 2 phenyl, 1, 2 ethene diol, right? If I add the numbers, I would have 2 plus 2 plus 1. That's 5. Now, if I number it like this, what I will have is 1 phenyl, 1, 2 ethene diol. And that would be 1 plus 1 plus 2. That will be 4. And always I have to choose the numbering that gives a lower sum. That is what I have to. That is why we number it like this. So essentially we have 1, 2. Now the parent name here, of course, will be ethene diol. It will be 1, 2 ethene diol, right? Or ethylene glycol. And then the phenyl is on position 1. So we say it is phenyl ethylene glycol as a common name, or as a systematic name, we say it is 1 phenyl, 1, 2 ethene diol. This is too much chemistry. Too much. But this is a bonus for you because you've watched the video. Bonus. Right. Now we add it to the acid. Of course, it's acid catalyzed. There's supposed to be temperature, which is not shown here. Now, what will happen? This is how the acid is. Oh, this is how the acid is. H here. There's H here. There's H here. There's plus here. The electrons will come and take the hydrogen here. The bond will break onto the side so that we can form water as a side product. So you see in both instances, water is formed. Now, this can also happen for this. So the two pathway, the first one, if you are moving, if this is 1 and 2, right now, the first one is when we have protonated carbon 1. And this is when we have protonated carbon 2. Carbon 2. Now, I told you as to which of the carbons have to be protonated, we will talk about as to which of the hydroxyl group have to be protonated. We'll talk about it. So that is where we are now. We have to talk about it, right? Now, if I protonate carbon 1 here, I will form O2 with water here, right? So water is here plus. Now, the water here is a very good living group. So it will break off on its own to introduce a positive charge on carbon 1. The carbon 1 that we have formed here, right? This positive charge. Now, this is a secondary carbocation. Secondary carbocation. Now, if you look at the side, if I protonate carbon 2. Now, when it breaks off on its own, because water is a good living group, it will break off on its own. It will introduce a positive charge on this carbon 2, right? Now, this is a primary carbocation. Primary because it's bonded, the carbon is bonded to only one other carbon. This is secondary because this carbon is bonded to two other carbons, right? Now, secondary is more stable than primary. So the secondary will form, but the primary will not form. That is why we maintain this. That is why we maintain this. And so always before you do the protonation, look at the hydroxyl group. That will give you a more stable intermediate before you even protonate, right? The more stable one you protonate, and then it will be lost as water to introduce the positive charge on a more stable cation, right? So that is the first step. So the protonation of the hydroxyl group is what we have seen here. Now the elimination of the loss of water to form the carbonium ion is what we have seen here, right? Now moving on to how we can transform from that to form our product. So from here, there will be a shift, right? Now, the reason why the shift is occurring, see, we are moving from a carbonium ion to carbonium ion, right? So essentially what we are doing is that we want to put the positive charge on the carbon that is bearing the oxygen, right? Or that's bearing the hydroxyl group. I'll explain why. So here, we would move the hydrogen. Now, the hydrogen here is going as a hydride, H minus. It means it's going with all the electrons. So the hydrogen here will jump. That is what we call the 1,2 skeletal rearrangement, or we call the hydride shift. The hydride shift. So we move here. Now, when it moves here, the new bond will come and form here. The positive charge will be transferred to this carbon. So that is what has been shown here, right? Now, the reason why we move from the carbonium to carbozonium is because this OH group, the oxygen there has lone pairs, and the oxygen can use the lone pairs to stabilize the positive charge to form a resonance structure. The first point that I ask us to take note of is the arrangement will occur quantitatively only if the new carbocation form is better stabilized by an intermediate, by a substituent, which is what we are seeing here. The oxygen in the hydroxyl group can better stabilize the carbocation. That is why the 1,2 shift will go on. That is why. Mm, 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 mm. And so, well, what we have here, right? What we have here will be the donation as has been shown with the blue, right? Donation of the electron now to. So there will be a double bond now after donation of the electron. A positive charge will be transferred onto the oxygen. Now this can go back and forth like that, right? When you have two resonance structure, you are more stable than the one that has none, right? If I have three resonance structure, I am more stable than the one that has two. And so the more the resonance structure, the more stable, right? Now this is why the shift will occur. This is the whole reason why the shift will occur. Because when you do the shift to form your carbozonium ion, the oxygen in the hydroxyl group can better stabilize the positive charge, the carbocation, right, to get a more stable intermediate. And I've already explained that reactions will always proceed to form a more stable intermediate. Now, when we get here, then we'll do the final stage. So when we get here, what will happen is that in order to stabilize this positive charge, the water here will come and remove this hydrogen, right? And then the bond here will break onto the oxygen so that we can have our hydrozonium ion here as we started with. So it will show that the hydrozonium ion is a catalyst, right? And then we will have our positive charge here neutralized so that we can form our carbonyl. Now let's use this understanding. Let's use this understanding to go and then do the mechanism for pinnacle rearrangement to pinnacle. So let's go up quickly. Let's go up. Let's draw pinnacle. This is pinnacle. This is pinnacle. C OH, C, OH, CH3, 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 CH3. Now we have the acid. This is always my hydrozonium ion. This is the acid. Now what will happen? First step, protonation. Protonation of the hydroxyl group. Which of the hydroxyl group do I have to protonate? Now the environment for this one is the same as the environment for this one. The environments are the same, right? So this one has CH3OH. This has CH3OH, and this, so the same. So we can protonate any of them, right? So let me just protonate this. Now what will happen is that the OH group here, the oxygen there, the lone pairs will come and attack the hydrogen here, and the bond here will break onto the oxygen here. So my side product formed will be water. Water will be my side product, and then this whole compound, the pinnacle here will be protonated. So I'll have something like this: CH3, C, OH still here, CH3, C, CH3, CH3. Then I will have OH2 plus. When the oxygen forms an extra bond, so 3 bonds now, it would bear a positive charge, right? Now, this whole group here is a good leaving group. So what will happen is that it will break off on its own in the next step. Break off on its own so that we can form this. We'll form CH3, C, OH, CH3 here. We come down here, we'll form CH3, CH3, and then a plus sign here. So this is our carbocation. Now, at this point, there will be an alkyl shift. We call this one, because it's a methyl group, a methyl shift. Essentially to change it from a carbenium ion to a carbozonium ion. So we will have a shift here, an alkyl shift. Right? Sorry, yeah, an alkyl shift, a methyl shift. The methyl is a specific alkyl group that we are talking about now. So we'd have something like this. CH3, C, OH, C, CH3, CH3. Now the CH3 will move here, so CH3 will come here, and then the positive charge will be here. Now I've explained that the reason why this has to occur is because the oxygen here has lone pairs, right? They have lone pairs, and this lone pair can be contributed to stabilize this compound. So that's what will happen in this step. We will have the lone pair being contributed to this one, so that as a resonance structure, look at the arrow I'm using here, resonance structure, the same structure, different tariff, same structure. CH3, C, this is CH3, CH3, CH3. Oh no, I've jumped one. So C here. Sorry for that. There's okay. So now what will happen? This is the C. This is the C. Okay, let me clean it and draw it well because I'm showing reaction mechanism. Okay, right. So this one here, the O here, the H here. Now, because of the new bond here, I would have a double bond here, right? And the plus sign on this one. And that will be it. So the plus sign has moved from this carbon and now into the oxygen. And this is what we call resonance. Now, in the last step, what will happen? For me to know what will happen, I have to now separate this hydrogen, because that's where the reaction will happen. So let me just redraw this hydrogen, clean the hydrogen, the same thing, but expand the bond. So in the last step, what will happen is that the water in the medium, the water was here, right? The water in the medium will come and attack the hydrogen. So water, the lone pairs on the water will come and attack this hydrogen. So we'll come and remove this hydrogen. And then this bond here will break onto the oxygen to neutralize the positive charge. So in my last step, to form my pentacolon, I will have this CH3, C, double bond O with no positive charge again, right? double bond O with no positive charge again. Now we have CH3, 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 and that is that for that. So now I'll form my pennacolumn from the pinnacle. Now, if a question is supposed to come around this, first of all, they will give you pinnacle and give you the condition and ask you to predict the product. So quickly, you have to know you form pennacolumn. You have to be experienced before you can predict this product. Even the last example that we used down there, it wasn't pinnacle. But you see, there were a lot of skeletal rearrangements. So if you want to look at the structure and you don't look at it twice and you want to predict the answer, you get it wrong. So you have to take your time when it comes to this whole chemical process, the pinnacle rearrangement thing. You have to take your time. You have to take your time. You cannot rush. And you have to practice the mechanism. You get the mechanism by practicing. Practice, get it wrong, go back, refer. Practice, 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 practice so that your eyes know, your head know, and even your hands become familiar with the method. That's that for that. Very simple. This is how we form pinnacle from pinnacle. Let's quickly go and then conclude the whole topic. Let's go and conclude the whole topic with the last step. So this is the last mechanism that we'll talk about, right? The first mechanism, we have a glycol, ethylene glycol, and then we are adding PBr3. And what will happen essentially now, the only thing that you're expected to know here is how we can transform the reactants to product. So the OH here will move away, OH here will move away, we'll put Br there, Br there, and then we have ethylene dibromide. That is how we do it. Now, the next one we have the ethylene glycol plus acetic acid. Now, what is happening here is an esterification reaction to form a very sweet-scented product, right? Esterification reaction. And so what will happen in essence? Let me draw the whole thing again so that we can see it well. CH2OH, CH2OH. Now, acetic acid. So this is acetic acid. CH3, COOH. That is what we have. CH3, COOH, right? So what will happen is that OH will move away from here and H will move away from here, right? And there's a direct coordination between this. The actual bond is formed between, this oxygen here is double bond O on this carbon. So the actual bond is between this carbon and then this oxygen. It's between, let me change the ink. The actual bond is between this carbon and then this oxygen, right? And so if I'm writing the product for the top there, I mean at the top there, I would have CH2O. Now, if you want to be technical, it's C double bond O, CH3, right? Yes, down there, I will not be technical. So now the same thing will happen. The H will move away from here. The OH will move away from there. So if I'm writing it, it will be CH2O, right? So from here, CH2O from here, the H is no more there. Then I have to turn it. So I'll have COCH3. Now I can still make this O because the O here in front of this one is double bond O. So yeah, I can write it there and then remove this one, just as I did. Or I can just simply leave it like that. Let me just leave it like that so that I'll have two different ways of representing. So leave it like this. I'll leave it like this, CO, right? So this is the ester. So this is a diester, right? Diester, ester here, glycol diacetate. That's ethylene glycol diacetate. Very simple. Now the last one is how we form our dioxolane, right? And that is very simple. What will happen is that we will lose an H from here. Now we'll lose the oxygen from here. So the two H's and the oxygen can essentially be extrapolated as the water here. That's not the mechanism. That is just how we can predict the product. And then now the double bond here, once it's broken, this carbon can form two bonds. One of the bonds with the oxygen here and the other bond with the oxygen here. So it gives you this cyclic compound. Very simple. So these ones, you have to know how to predict or write the products from the reactant. And this is all we need you to know. Now that brings us to the end of the discussion on glycols. And as it goes, this is not a supplementary and this is not an alternate material to what we are doing in class. This is just a supplementary material to add up to what we are doing in class. And if you have any question, you can either see me or see any member of the HESA academic board. Thank you very much for being with us. And then May God be with us.